The topic of today's lab is projectile motion. The aim is characterize the given charge the launcher in the vertical direction and build up setup for hitting the target at some distance. The equipment we used is a dot launcher, a ruler, and a projector. Okay, these are the methods we used. First of all is measure the maximum height of the cannonball reaches and in the vertical direction. Then we calculate the initial velocity of a cannonball. And we find the equation that shows the relation between the horizontal distance and the launching angle. And last one is calculate the launch angle for hitting the target. How we measure the vertical height? It is we use a launcher attached to the floor and a ruler as well. Then we shoot out the cannonball, and we just take down the highest point, the highest distance it reaches, and we just mark down the distance on all the numbers, which is 1.2 meters, 1.23, 1.25, and 1.21 meters. The uncertainty we measure we define as 0.05 meters. And then we use the formula for vertical projectile motion, which is V equals to a square root of 2 times G times H, which is H is the highest point it reaches. Then the maximum is square root of 2 times GH maximum, and the velocity minimum velocity is square root of 2 times 3 times H minimum. The height we just marked down to calculate the velocity, the initial velocity of the cannonball, and we get 4.85, 4.91, 4.95, and 4.87. The uncertainty is 0.1 meters per second. We are going to modeling the projectile motion. This is the angle. We just put the launchers here, dot launcher here on the floor, and we just going to hit the target on the floor as well. So the cannonball has an initial velocity, which is V here, and just separate it to the horizontal direction, which is Vx, and the one for the vertical velocity is Vy, and angle with angle theta here. And the distance between the target and the launcher is r. And we knew that the t is equal to r divided by Vx, which is the velocity on the horizontal direction. Velocity on the vertical direction, the initial speed has the negative value with the final speed, which is Vfy equals to minus Viy. Vx and Vy respectively we get using the velocity here, v, which is the initial speed. We can calculate it as Vx equal to cosine theta times v. Vy is equal to sine theta times v. Vertical projectile motion, the final speed, the negative value of the final speed is equal to the final speed here, is equal to the initial speed minus gt. And we know the final speed is equal to minus the initial speed in the y direction. So we get minus yv equals to minus Vy equals to Vy minus gt. We know that t here is equal to r divided by Vx. So we get g times r divided by Vx equal to 2 times Vy. And we simplify this one, we get r equals to 2 times Vy times Vx divided by g. And we replace sine theta times v and cosine theta times v to Vy and Vx. So we get this equation here, and we just get it because of 2 times sine theta and cosine theta is equal to sine 2 theta. Then we get r equal to sine 2 theta times v squared divided by g. And so transform into this equation here. And the last step is calculate the launching angle. We get r equal to 2 meters. So we get 2 meters equals to sine 2 theta times v squared divided by g. And we know the v is equal to, we could just calculate the v, which is this value, and r here. So we can calculate out the theta easily. Then we still have the uncertainties. So theta, the maximum theta is equal to this one, and we get 27.61 degrees, and the theta minimum is equal to 27.28 degrees. The theta is equal to 27.445 degrees plus minus 0.165 degrees. Then we just set up this angle here, this angle, then we can hit the target. So in conclusion, by measuring the maximum vertical height and constructing the Vancouver modeling, we can set an angle to hit any target within range.